Dear students, hope everything is fine at your side. Today, in this lecture, I shall mainly discuss about the advantages of nanoparticles over bulk, and then later on in different two parts, I will mainly discuss about two very important phenomena related to nanostructured materials, that is quantum confinement effect and surface plasmon resonance. Whatever I remember till now, in our previous classes we have already discussed about the introduction of nanoscience and nanotechnology, or else I think we have almost discussed about some introductory part of nanoscience and nanotechnology, right? Or if you do not remember, then you can follow any introductory book or any kind of introductory chapter, maybe in internet or means any kind of book, okay, for this purpose. So here mainly whatever I am going to discuss in this particular lecture is nothing but it is about the surface to plasmon ratio. So in this particular part 1, I shall be discussing about the surface to volume ratio, okay. So before going to discuss about the surface to volume ratio, of course we should have at least some preliminary idea about the nanoscience and nanotechnology. So for your just remember, I can giving you one small definition of nanoscience and nanotechnology first, then I can go to the main part of this particular lecture, that is surface to volume ratio, okay. So what is basically nanoscience is? Nanoscience is the study of systems in nanoscale, and nanotechnology is the ability to systematically organize and manipulate properties and behavior of matter in the atomic and molecular levels. What does it mean? Whatever the definition said here for the nanoscience and the nanotechnology, what does it mean? It means whatever is the system, if any one dimension of such system fall under 1 to 100 nanometer range, then the study of such systems is known as nanoscience, okay. On the other hand, suppose if you develop any process, okay, by using which you can tune any properties of nanomaterials or make any useful products such as suppose electronic devices, catalysts, sensors, etc. So those processes will be called nanotechnology. So basically the nanoscience is the study of a particular system, and nanotechnology is the kind of means development, okay, study about those particular processes, okay. So that is the basic definition of nanoscience and nanotechnology. Now of course second question can come to your mind is something like, why nano? What is the purpose of means studying all those particular nano and nanoparticles and all these things? So of course the question will be how it is different from the bulk means, how it is advantageous means, okay, how nanoparticles or nanosystems are advantageous over the bulk. So some basic differences or some advantages of nano over bulk you can find anywhere, any basic books you can follow, or even anywhere you can get the advantages or small differences of these nanoparticles over the bulk particles. Like here you can see that this one is in the case of bulk materials, this bulk materials have higher melting point, okay, but when you compare it with their nano counterpart, then melting point you will get is lower in the case of this nano, right? Then in the second point you can find here, see, it is rapid result with small sample volume. It means you will use small amount of volume, small amount, but whatever the result you will get, that will be very effective result means, okay, more result means you will get, but using by using a small amount of volume, okay. So for any purposes means if we use very small amount of even small quantity of this nanoparticles, then also that is sufficient for that can even solve the purpose, okay. After that, another special feature of nanomaterial is when you see the percentage of total number of atoms or ions on the surface of nanomaterial, it is always high compared to the bulk one. Okay, so if you calculate suppose the percentage of atoms at the surface, okay, if you compare the percentage of atoms present at the surface in the case of bulk material, it is always lower than the nanoparticles, where the percentage of surface atoms, where the percentage of atoms present in the surface is always more. Okay, so it means you always have to compare the surface atoms with respect to the volume means. Okay, in the case of bulk, although the volume is high, very high, okay, in the bulk material you will have the high volume. So that is how if you calculate the total number of or total percentage of the whole atoms, okay, present there in that particular whole bulk material, then in that way compared to that particular atoms, of course with respect to that total percentage of atoms, you will have lesser number of atoms or lesser number of means ions present at the surface. But in the case of nanomaterial, if you see the volume is very less, right, very less volume in the case of nanomaterial. Okay, so if you calculate the total number of atom or ions present there in the nanosystems, okay, so with respect to that particular total percentage of atoms, whatever the surface atoms or whatever the number of atoms or ions present at the surface you will get, that will be of course very high in the case of nanomaterial compared to the bulk. So that is one very important point here you always have to remember in the case of while differentiating the bulk material with the nanomaterial. Okay, so why high percentage of surface atoms or ions are benefited? Why means if you have more number of surface atoms or more number of atoms or ions at the surface, why it is more beneficial? So the answer is, it is because these particular surface atoms or ions are mostly regarded as active sites actually. Okay, those are the main active sites for any kind of means applications. Okay, suppose if you suppose kind of catalytic applications, if you suppose any kind of means biological applications, okay, main we try to understand or try to study about the interaction of that system, interaction of any kind of substrate with the surface atoms. Okay, that is how those particular surface atoms or ions are always regarded as mainly the active centers or active sites. So of course if you will have more surface atom, more percentage of surface ions or atoms, then of course you will have more active centers, more active sites, of course that will be more beneficial over other. And that is how if you compare the reactivity for any kind of reaction, suppose, of course, okay, so if you can if you compare the reactivity of bulk material with the nanomaterials, of course the reactivity of nanomaterials are always higher than the reactivity of bulk materials. That means nanomaterials are always highly reactive means than the compared to the bulk material. Another important point you can remember here, you can see here in this particular point is nothing but the tunability of properties in nanomaterials means, okay, that particular property is very important in the case of nanomaterials. That means we can tune any kind of properties. If you take suppose the mechanical property, if you take suppose some kind of electrical property, any kind of suppose mechanic or any kind of suppose optical properties, okay, electrical properties, optical properties, mechanical properties, all those particular properties can be tuned as per requirement by tuning the size and shape of the nanoparticles. Okay, so whenever you will tune the size and shape, or whenever you suppose increase or decrease the size of a particular nanomaterials, okay, accordingly of course you will tune or you will obviously change some kind of surface properties there, and of course that particular surface property will change whole properties means different types of properties there in the nanomaterials. Like optical properties, it can affect the optical properties, it can affect the electrical properties, it can affect the mechanical property. So that particular tunability of properties is very important in the case of nanomaterials, and by tuning or by changing some kind of size and shape only we can actually tune any kind of properties in the case of nanomaterials compared to the bulk materials. So you can say that in the case of bulk material almost whatever the physical properties, whatever the mechanical properties you will talk about, whatever the chemical properties you will talk about, that will be almost constant. Okay, that will be remain constant means. means at that particular range, if you change some kind of size or shape there, okay, suppose you will change some kind of size by 1 centimeter or 1 millimeter or even 1 meter type of things, okay, so in that way it cannot change its property. Whatever the original property it had initially, that will be remain intact, okay, in the case of bulk material. But in the case of nanomaterial, if you even change the size by even 1 nanometer or 2 nanometer, it can even change the whole properties, means various types of properties there in the case of nanomaterials. That is how it is very interesting, means that is how it is very interesting to study about the nanomaterials, means over the bulk materials. So those are the main advantages, small advantages or small differences you should always keep in your mind, okay. Then finally and most importantly, one great feature or you can say one great advantage of nanomaterial is its high surface to volume ratio, okay, although many times we just call it high surface area only. That means advantage of nanomaterials over bulk is its high surface area. We normally say that, okay, if somebody will ask you some questions about the advantage of nanomaterials, then we normally say that the surface area of the nanomaterials is actually high compared to the bulk material, but using only high surface area is actually wrong, okay, and always we should use some kind of means high surface to volume ratio. That particular term we should always use. So in the case of nanomaterial, whatever the advantage of nanomaterial over the bulk is high surface to volume ratio. We always use the term high surface to volume ratio, not only the high surface area. Suppose here if you see one smaller particle and compared to the smaller particle, if you see a bigger particle, of course you will see larger volume here in the case of bigger particle compared to the smaller particle, okay. But when you calculate the surface area with respect to the volume of this particular particle, then you will get to know that how the surface area is actually with respect to volume, how surface area is actually higher or bigger in the case of these smaller particles compared to the particular large particles. So here from these examples I hope the concept will be more clear, okay. Suppose here this one is the smaller particle, this one is slightly bigger compared to this one, and this one is the biggest particle, okay, here among these three particles. Now if you suppose the side of this particular particle is suppose 1 unit, okay, this one is cube, this one is also cube but bigger cube, and this one is the means the largest cube, okay. So if you suppose assume the side here, one side, okay, one side is suppose 1 unit, okay, then you can calculate of course the surface area here by using the 6a square formula, 6 side square formula, and of course the surface area will be your 6 only, 6 unit square only, okay. Then you can calculate the volume also, that volume will be of course the a cube. So whatever the volume you will find, that one will be 1. So finally if you calculate the surface to volume ratio, means with respect to volume when you calculate the surface area, then it will come out to be this one 6, okay. So similarly if you suppose calculate the surface area for this bigger particle, okay, this one is just nothing but it is just 2 times higher than this particular material, okay, this particular means cube from all the sides, okay, everywhere it is actually just longer by 1 unit. So that is how all the sides from here, everywhere, all the sides it is assumed to be this 2 unit. So if side is 2 unit, then of course the surface will be the 24 by using the formula of 6a square, okay. So volume will be your a cube, so it will be 3. So when you calculate the surface to volume ratio for all these particles, so you can easily imagine that how the surface to volume ratio is actually large in the case of these smaller particles, then this one and then this one. Accordingly, in this second example, you can suppose all these cubes, all these cubes volumes are same. So you are doing nothing but you are keeping the volume same here, okay. You are taking such type of nanoparticles where the volumes are absolutely same, okay. So here in this particular case you are having only one particular cube. So for this particular cube, if you calculate the surface area suppose this side is nothing but it is again 1 unit. So if you calculate the surface area for this cube, single cube, then it will come out obviously the 6a square into 1 cube. This one is nothing but it is for the 1 cube. So of course whatever the surface area you will get, it will be the 6 unit square. But similarly, by keeping the volume same, if you divide this cube into these parts, okay, 1, 2, 3, 4, 5, 6, 7, 8, that means you are doing nothing but you are making 8 cubes by keeping the volume same. Means you have just divided this particular cube into 8 cubes, 8 smaller cubes. Then if you calculate the surface area for all these cubes, what will be the surface area? Then the overall surface area you will get is of course nothing but for 1 cube it will be 6 into, of course the side will be now half of this particular side, so it is kept here is the half, so half square, 6 half square, and you are having total number of 8 smaller cubes, so you are multiplying this whole term with the 8, so that is how it will come out 12 unit square. Accordingly, in the case of surface area for this particular cube, okay, you have divided this cube into even how many numbers of cubes? Total number 27 number of smaller cube. So finally, whatever the overall surface area you will get for this cube, although the volume is absolutely same with this particular cube, but whatever the surface area you will get here, it is the 18 unit square. So just by dividing this bigger cube, means one single cube, into smaller cubes, okay, keeping the volume same, you are getting actually more surface area. Okay, so that is how, in that way you can prove that smaller particles, how smaller particles can give you more surface area, and how this more surface area can be effective for various applications. Now in a different way, if you suppose measure the mass of all three these cubes shown in A, B, this one is A, B and C, you can easily imagine that the mass of all these three will be actually same. Okay, mass of all these particular cubes are absolutely same, but by increasing the surface area of this, by increasing the smaller divisions here, okay, for these particular cubes, you are doing nothing but you are increasing the surface atoms also. Here you will have more smaller divisions, then here and here even you will have even more divisions, even more smaller divisions here even compared to this one. So more smaller divisions means more will be the surface atoms. So of course more will be the surface area, more will be the reactivity. So that is how this one will be more effective for a particular reactions, or more reactive for a particular reactions compared to this one and then this one. Now in a similar way you can discuss this surface to volume ratio in the case of this spherical particles also. Here this radius of this spheres is supposed to be small r, or for this one is capital R, this one is capital R1, and if you calculate the surface area by using the formula 4 pi r square, and if you calculate the volume of the sphere by using the formula 4 by 3 pi r cube, then of course finally you can calculate the surface area to volume ratio, and whatever the surface area to volume ratio you will get here for the spheres, it is nothing but the 3 by r. What does it mean? If the surface to volume ratio is 3 by r, that means it is depending upon the r. Okay, so when you will increase the r, of course the surface to volume ratio will be less. So that is how in the case of bigger particles, bigger spherical particles, whatever the surface to volume ratio you will get, that one will be of course the less compared to this one than this one. So of course in this particular case you will get actually more surface area, more surface to volume ratio in the case of spherical particles also. So for any kind of particles, whether it is spherical, whether it is cubic one, anything else, any particular particles, by just decreasing the size of the nanoparticles, by decreasing the size of that particular particle, you can just increase the surface to volume ratio, and by increasing the surface to volume ratio you will have more number of surface atoms or you can say that you will have more numbers of atoms or ions at the surface. So that is how you will have more active sites, and that is how those nanoparticles will be having more actually catalytic properties over the other means bulk particles. Okay, so that is how you can say that nanoparticles are even more reactive compared to the bulk one. So whatever I have discussed till now in this particular lecture, from this lecture what we understood so far is, when a given volume of material is made up of smaller particles, the surface area of the material increases. Second point, when the particle size decreases, a greater proportion of the particles will be found at the surface of that particle, which leads to nanoparticles with higher reactivity, as I have already discussed. And then third point you can remember here is, when chemical reactions occur between particles that are on the surface, a given mass of material made up of larger particles will be very less reactive than the same mass of nanomaterials. That means you may have the mass of a particle same, but depending upon the size of that particular particle, the reactivity will be varied. So for your information, I am giving you some references here. So if you want to study in more details for this particular topic, you can follow these references. And finally, of course, all the best and happy learning.